Okay. Okay, so thank you very much. It's nice to be here. So I was a PhD student of Oscar there in Córdoba. So I spent some time there, and we continue some of this work in some of the postdocs. So the things I want to discuss today are essentially this work we did during my PhD. In the context of the dynamics of plasma around compact objects like black holes or neutron stars. So this is a code originally written by Oscar himself. I mean, the original infrastructure, especially the grid infrastructure, which is the most interesting thing about the code, maybe. So I started with this original version of the code, which was computing essentially the equations of vacuum electrodynamics, or, well, generally Maxwell equations, on this grid infrastructure. I will discuss later. And during my PhD, we were focusing on studying or accommodate this code for studying these astrophysical plasmas around compact objects. So it's involves like a slight modification of the Maxwell theory, but quite similar, as we will see soon. So I adapted the code during my PhD for this reason. So the plan of the talk is to motivate first by providing some of the astrophysical context to this modified Maxwell theory, which is meant to represent the plasma field magnetospheres in this astrophysical scenario, like pulsars or AGNs, which are like active galactic nuclei. So involving supermassive black holes in the center of the galaxy. So I will try to start justifying this approximation, this plasma approximation in these scenarios, giving some of the brief description of these astrophysical settings and so on. And then I will discuss more intensively about this particular PDE system we want to evolve, this force-free electrodynamics. Is a modification of Maxwell theory, and in particular is a nonlinear theory. So it has some subtleties in the formulation and some of the regarding its well-posedness. So we did some analytical and some theoretical studies to begin with before to really implement the code numerically. I will discuss briefly about the constraints of the theory. And then I will, the next section is about the code itself. So I will briefly summarize the main features, description of the code, and then we will probably take a tour to the code. Later, I will discuss some more in depth about the boundary conditions, which was some also analytical aspects in the implementation of these boundary conditions to represent, in particular, the perfectly conducting surface of a neutron star. We want to represent the surrounding of a neutron star at some point, and so for that we needed to represent appropriately the boundary conditions of the neutron stars at the neutron star surface. So I will discuss this a little bit more, and then I will show some of the numerical results throughout these years. In regarding pulsars and also different settings involving these compact objects, and I will end with the last, which involves we adapted this system for this code to evolve a binary system for So in particular, a black hole orbiting a neutron star. Okay, so perhaps a small disclaimer. So the presentation is constructed. I didn't have really much time to prepare in depth this presentation. I should confess. But the idea is to use some previous talks I gave in the past, essentially 2 talks, one from 2019 especially, and another one more recent, covering these pieces. And in the middle, I will give this tours. I will show some parts of the code itself. But okay, so these talks, one of these, especially the more like analytical parts, are maybe I'm a little bit rusty. So the idea is that you can stop me at any point to ask questions, and also Oscar, you are more than welcome to contribute and trying to connect with the concepts you have been seeing in the course, right? Okay, so that's the idea. So let me start with some motivation. Sorry. Oh, this one. So the motivation is essentially the main astrophysical settings we were interested was one is pulsars, which are neutron star, spinning neutron star.
Fede, can you increase make it sort of a presentation so that we can see better in at the screen? Good.
Is that good enough, or?
It's okay.
Because since I will be jumping from one presentation to the other, maybe it's
okay.
Is it okay, or should I present?
Yeah, maybe it's better if you present.
Okay. Let me see.
Okay.
Okay, so some many relevant scenarios in astrophysics involves a tenuous plasma surrounding a compact object. And one or two main examples, I mean, historical examples are pulsars, which involve a rotating neutron star. So a neutron star is a very, very compact object. The next following the black holes, which are the most compact objects in astrophysics. The next are neutron stars. Neutron stars possess typically very intense magnetic fields also. And pulsars are very well known in astrophysics. They play a really important role because they produce these very precise pulse emissions, electromagnetic emissions, which are very, very steady in the sense that they have the same period for quite some very long times, very stable objects, and so very interesting objects. And the other scenario that involves this tenuous plasma, which has this description of a tenuous plasma surrounding this object, has helped in understand the mechanism, the astrophysical mechanism for extracting this energy from the central compact object. For instance, in this case, the rotational energy, to be emitted or be reprocessed in the surrounding magnetosphere to produce electromagnetic emissions, which are these signals we see, these pulse emissions from pulsars. And also in the active galactic nuclei context, as I mentioned, there is a supermassive black hole in the center of the galaxy. The galaxy would be this very little dot here in the middle. And you see these enormous jets emerging from the central object, from the galaxy. So these jets carry very, very huge amounts of energy. And it was for some time a mystery how this energy can be extracted from the from the source, from the central black hole, and what are the details of this mechanism for extracting the energy. And so later, so now I want to argue that force-free electrodynamics, force-free approximation, has played a central role in understanding these two systems. And so, okay, this is a little bit of a detour maybe, but I'm trying to give some motivation and some astrophysical context for the code. So this is some like historical highlights of the developments of these fields. So in particular about this, the role played by the plasma and how it has allowed to understand the energy extraction mechanism in the two cases, in the case of the neutron star and in the case of the black hole. So in the context of pulsars, we have these main historical ideas by Goldrich and Julian. They realized that if you assume a vacuum, so no charged particles, no electromagnetic source around the neutron star, and you solve this problem, assuming, let's say, the star has a magnetic dipole, the neutron star surface is a perfectly conducting surface, and the star is rotating, as spinning, as we saw. So you can solve the electromagnetic field in vacuum surrounding this configuration, and they realized that there should be a very strong electric field along the magnetic field lines, and that for the very strong magnetic fields the neutron star has, this energy should be very strong as to pull charged particles from the stellar surface. And moreover, or later, additional process can also occur to produce a cascade of particles and antiparticles, electrons and positrons, that start filling the surrounding star with this plasma. So in a sense, they realize the vacuum outside these objects is unstable, in the sense that any charged particle around, either extract from the surface or produced by this particle cascade, will start populating the surrounding with this plasma, and the plasma, as long as it's beginning to be generated, it will try to screen this electric field component along magnetic field lines. So at some point, this mechanism will regulate itself, and it will stop producing the plasma. And okay, so then the idea is that physically, force-free electrodynamics, or the force-free approximation, is a tenuous plasma, in the sense that there is enough pairs to screen the electric field, the Lorentz force, but the inertia of this plasma is very, very small compared to the energy of the electromagnetic field, and in particular the energy of the magnetic field. So this plasma will behave, in a sense, will be dominated by the magnetic field and will obey a particular dynamics we will explore later. But the point here is to argue why this plasma is expected around these objects, and why the force-free approximation is justified in this context. So in the case of the black hole, similar idea was considered. If you assume vacuum around the black hole, a rotating black hole, Wald actually solved a very elegant, he found a very elegant, exact analytic solution for this, based on the two killing fields associated with the space-time. And this electromagnetic field, again, possesses this very strong electric field along the magnetic field lines. So the argument is similar. In this case, we do not have a star surface to extract directly the charged particles, but the pair creation process is very similar. The idea is that any charged particle around will be accelerated by this electric field along the magnetic field lines, and these will produce photons. These photons will interact again with the magnetic field to produce create a pair of electron and positron. Each of these electron and positrons, they will be accelerated again, and so on and so forth, producing this plasma. So this idea was completed by Blanford and Snaik, again, that the electrovacuum around the black hole would be also astrophysically unstable. And it will lead to a magnetosphere field with this tenuous plasma around. So then these ideas were also, complemented. This is not the whole story. Then the idea is that this tenuous plasma around can help in understanding the extraction mechanism, namely the extraction of the rotational energy of the central compact object to be transferred to the electromagnetic field, to the plasma, to the surrounding plasma, right? So in the pulsar, again, in the neutron star context, is rather simpler than in the black hole, as usually. And here there is very classical idea in Landau-Lifshitz book. The idea is that if you have a magnetized sphere which is rotating, then electromotive force will be induced in between the equatorial point B and the polar point A, right? So if you can close this circuit, you can connect by a conducting media the points A and B, then you can, and you have some dissipation in this circuit, this energy dissipated there will be fed by the energy extracted from the rotation of the object. So there will be a torque slowing down the motion of this sphere, and you will extract electromagnetic energy from the system. And that is the classical picture underneath, behind the pulsar magnetosphere. The idea is that this plasma around the neutron star plays the role of the conducting media. So this induced electromotive force can be conducted away to the surrounding magnetosphere. And there are some regions, in particular this region producing pulsar, which is known as the current sheet. So I'm trying not to enter much in the details, but there is essentially the structure of the pulsar is that there is an inner region that can co-rotate with the neutron star. So there's a plasma that can follow the rotation of the neutron star, but that only can happen up to some point called the light cylinder, which separates, so the region in which this co-rotation implies the velocity of the speed of light velocity. So the plasma outside this light cylinder can no longer co-rotate with the pulsar. So the magnetic field lines there open up and produce, in this opening up of the magnetic field lines, produce this continuity layer here, and produce this current sheet, which is a very strong electric currents circulating there. And these are the regions where dissipation occurs in the magnetosphere. And this dissipation is extracting, the energy dissipated there is coming from the energy which is extracted to the neutron star rotation. And that's why this is usually known as the spin down luminosity. The luminosity that you can extract by the plasma in this system is known as spin down luminosity, just because it is slowing down the motion of the neutron star. Okay, so this is more or less classical idea, and this was the core of the development in pulsar theory, and this is very important role played by the force-free electrodynamic in this sense. In the black hole case, as I mentioned, it's slightly more subtle again, but the idea is similar. It is relies on some process known as Penrose process. So in principle, as you might have heard, the black hole horizon, nothing escapes from the black hole horizon in principle. When the black hole is spinning, there is an external region to the black hole, to the horizon, known as ergosphere. And in particular, in this region, let's say the energy of a test particle as measured from a distant observer, within this region, you could have a negative energy for these test particles. So the idea of Penrose was that if you manage to send a particle, let's say with the initial energy E0, inside the ergosphere, and inside and this particle splits into different particles, one falling into the black hole and the other one escaping. That process is totally possible by the linear momentum and energy conservation. And if you tune this in a way that the energy of the particle falling into the black hole to be negative, as I mentioned, this is possible inside the ergosphere. So then what will happen is that the emerging particle, let's say with energy E3, will possess a larger energy than the initial particle. So that means, or it could be interpreted as energy being extracted, and this will reduce the angular momentum of the black hole. So in a sense, is energy extracted, rotational energy of the black hole extracted, carried away. So the idea is that this plasma can help in produce this effect through this electromagnetically and through the presence of this conducting plasma. Okay, I'm not going much into the details, but this is, I mean, conceptually, this is the idea that you have this conducting plasma. It will change the configuration from the vacuum one, and you will have field lines that enters the ergo region and can extract energy from the black hole. So in the case of the AGNs, it has also shown that this can produce the collimated jets that were seen in these kind of systems, this kind of scenarios. Not only the energy extraction mechanism being explained by the force-free, but also the collimation and the production of the jet that was understood more or less, the principles. So far, so good. There are some questions, comments. Okay, so now the idea is to jump a little bit to the code. No, sorry, not yet to the code. Sorry. So I need to switch. So then, so I more or less try to say physically what force-free electrodynamic or force-free approximation was. So as I mentioned, it involves a tenuous plasma that is dominated by the magnetic field. And what happens with the plasma in such condition is that the plasma, these very light particles, electrons and positrons, will very quickly accommodate locally to screen or cancel the Lorentz force locally. So this is the dynamically what this plasma in this regime is typically doing, and this mathematically we can see how is this derived and what it means mathematically. So here I'm starting with the electromagnetic equations, Maxwell theory. Sorry, I didn't mention that. So these talks originally were prepared for the audience within GR community. So maybe there are some concepts from GR which I will try to emphasize maybe, or try to explain a little bit, but it's hard to go into the many of the details involved in this GR aspect, right? So these are how the equations of electromagnetism looks in GR. This is usually known as general covariance. They are written in a way that, I mean, equations in GR are expected to be invariant and invariant for any coordinate transformation. So this index here, A and B, represent space-time indices. F here is the electromagnetic tensor, and the Y here is charge. It represents the charge density and the charge currents of the source in the electromagnetic equations. And the nabla here are the covariant derivatives of the system. So it's a first-order linear system with sources codified in this tensor here. So the idea is that, as I mentioned, the conditions for this plasma is that this is the total stress energy tensor. This has the information on the energy, the linear momentum, and the stresses of the system, of the matter in general, which in this case will be constituted by the electromagnetic stress energy tensor and an additional component associated with the fluid, right, with the matter itself, which in principle are coupled through these electric charge and currents. But the point is that in this approximation, the electromagnetic stress energy tensor completely dominates over the inertia of these plasma particles, so that the total stress energy tensor is approximately the electromagnetic stress energy tensor. And the equations follows from the conservation of the total stress energy tensor, is this equation here, which under this approximation leads to the vanishing of the local Lorentz force. This represents the local Lorentz force, and this is a result of the approximation or the assumptions we made. And this has very important implicances in terms of the algebraic implicances in terms of the electromagnetic tensor. There are two invariant quantities constructed from the electromagnetic tensor, namely, well, the contraction between F and F dual, and the contraction with F with itself. And these two invariants, so one represents the electric field along magnetic field, and the other one represents the difference between magnetic field strength and electric field strength. And these are invariant quantities for any reference frame in which you define E and B. So these are usually said that the field is under this approximation, this condition is degenerate and magnetically dominated. But moreover, this condition here can be used to rewrite the equations, the original Maxwell equations, and to get rid of these source terms that was the coupling between the electromagnetic field and the fluid. And now, the price to pay is that now you have a nonlinear system for the electromagnetic field, but you don't have explicitly the presence of the the fluid. This is justified. I mean, the fluid is still there, but as I mentioned, physically what it's doing is something very simple. It's trying to screen the Lorentz force, so that this very simple behavior of the fluid, it's what makes possible this decoupling, and this information is codified in the nonlinearity of the system now. Of course, you can always recover the fluid degrees of freedom associated with the charge density and currents from Maxwell equation. So you can solve this system for F, for the electromagnetic field, and then you can take this covariant derivative and you get the four current associated with the plasma. So you can recover partial information of the plasma. The plasma is really there, but it's doing something very simple just so that you can decouple and simplify the equations. And typically, to close this system, you need to add, it's customary to add an equation. So now this is sort of a constraint. E dot B should be 0 always. So the idea is to add a condition like this that covariantly will read like this, equation 3. Okay, so this is our system at the covariant level, as I said, is now a modified version of Maxwell or electromagnetism involving nonlinear equations that, in a sense, are codifying the presence of this particular plasma. Okay, so what happens with the well post of this equation? So any questions on this part? I'm sorry about the GR details. I don't know if you want to say something more, Leko, about this or explain a little bit more.
I mean, you can think of the equations on flat space-time for the part of the initial value formulation, and everything is the same. So think about this nabla as partial derivatives. That's all.
Yeah, exactly. Okay.
In space-time.
You can particularize this for Minkowski for flat space-time, and this will be like usual electromagnetism. Still, I wasn't sure, is all of the audience physicists or
are people that are not physicists?
Okay. Because I mean, I was assuming electromagnetism was known, but I don't know if you want to add something more or.
No, it's okay.
Okay. So when we were starting to study this system, I was trying to implement this numerically. I had this infrastructure, very nice infrastructure in the code by Oscar. We realized that the system, if you formulate the system like the most natural or trivial way, you can formulate to write explicitly in GR, you typically need to split space and time. This is called the 3+1 decomposition. You choose your time, your space slices, and then you write explicitly the PDE system, the evolution system. If you do this very naturally, you run with this issue that the system seems to be only weakly hyperbolic. This is written in this, more standard language in Minkowski. We found this paper that explicitly point to this issue. But in the paper, they show that if you added terms proportional to the constraint, so in this system, the constraint is now no longer the divergence of E, which was originally in vacuum electromagnetism, but in linear usual Maxwell electrodynamics. Now the constraints are only the divergence of B and as I say, the scalar product between the electric field and the magnetic field. this is 0 for free electrodynamics. So this is the new constraint, algebraic constraint. This is the standard constraint in electrodynamics, divergence less of the magnetic field. So if you add these terms proportional to the constraints, you are essentially not modifying the physics, because these constraints are supposed to be 0 and remain 0 during the evolution. But if you choose these parameters carefully, they show that this system is indeed symmetric hyperbolic. So this is something that usually it can happen if you have constraints, and if you choose the formulation not carefully, you might even if a system is symmetric hyperbolic in the end, you might end up with a weakly hyperbolic system. So one needs to be careful about this. And since we wanted to implement this in GR, I mean with a non-flat spacetime, we wanted to evolve this around, for instance, a Kerr black hole. So we wanted to do this symmetrization to find appropriate evolution equations in the context of full GR. So we use this covariant approach by Robert Gerock. And this is the general definition of a symmetric hyperbolic system. You start with the quasi-linear first order system, can always be written like this. So here again, there are indices associated with the space-time. These nabla are covariant derivatives that you can think of a partial derivative if you want. And the phi here represents all your dynamical fields, or your fields. So alpha will represent all the index, the indices associated with the tensors of your fields. And this K here, it's the principal part, it's known as principal part. With this index, this capital letter index here representing the equations. This index is associated with the set of equations, while this alpha is the index of the fields, right? So in principle, you don't have the same number of equations as fields for systems that has constraints, right? So the system is known to be, is said to be symmetric hyperbolic if there exists an object, this H symmetrizer, that contracted with the K gives you a symmetric object in the index alpha and beta here. And if there exists a W, a covector, such that the bilinear form made produced with this H and the K is positive definite. So this is the general definition given by Gerock. So the idea is to find these objects for our system. And this, if you find this, then general local existence and uniqueness theorems apply, right? And you can guarantee the well-posedness of the system. So as an example, maybe it's not as trivial as I would like to, is Maxwell theory. So this, as I said before, these are the two Maxwell equation. Well, actually, this is Maxwell equation. This is known as Faraday equation, but the two of them makes the electromagnetism, classical electromagnetism. So we can read from these equations which one is K, the principal part. As you see here, is constructed from the metric and a totally antisymmetric tensor. So this is reflecting the fact that the theory is linear. So no fields in K. In principle, could be some. If the theory is nonlinear, K could be depend on the fields itself, but it's not the case for the linear theory of Maxwell. And well, for this, just as an illustration, you can find a family of symmetrizer parameterized by this vector t. This is the h, and with this h, you can construct this bilinear form that is, you can see that is symmetric in the index A, alpha, and beta. And also you can prove this is positively definite for any two perturbations here. Okay. So now this is our modified version of the theory. This is the first equation is the one, the nonlinear piece. The other one is the usual Faraday equation. And in yellow here, I'm adding additional terms, which I will explain now, actually. And the last equation is the one I mentioned, that to close the system, you need to add an equation like this, equation 3. So this is also included here to close the system. So one observation, as I mentioned, since this field, this theory is nonlinear, then the k depends on f itself. Okay. So before that, so this added field, this new variable phi here, is one technique to deal with the magnetic divergence free of the magnetic field. One of the constraints of the theory we have. And the idea is, let me show you this one. So this is the Faraday equation, and these are the new field included this way. And what guarantees that is that now the equation for phi is this equation. So this is the Nabla operator, the box. This is the typically wave equation for phi. And these terms can be interpreted as a damping term. This is not really necessary, but this guarantees, so now this field couples with the constraint, with the divergence of B. They are associated. Whenever this field is, when this field is zero, then it means that the divergence of the magnetic field is zero. But now it couples with this constraint and it propagates now. It has a non-zero propagation speed. And that is good because if you are, I mean, mathematically, the constraint is, if you start with satisfying the constraint, mathematically it will evolve. You can show it will evolve. It will remain zero mathematically, but numerically, any violation by some numerical errors that can accumulate at some particular part of the numerical domain, you start producing these violations, small violations of the constraint. And so these waves, what allows you is to propagate these violations, and in general to propagate them outside of the domain. I mean, to avoid that these violations accumulate in some particular region in the domain. And this additional term also helps in damping this violation. So this is a technique known as I forgot the name. Divergence cleaning is the name of the technique. You enlarge the system, you add an additional variable that couples with the constraint, and now these constraint violations propagate, and in particular you can also enforce them to be damped, so that helps in controlling numerically the violations, the possible violations of the constraint. So the point was to introduce that before going into the symmetrization of the system. So since this technique can be included at the covariant level, we included here before continue with the symmetrization a la Gerok. Okay. So sorry, maybe I wasn't very clear about this. Are there any question about the divergence cleaning idea? Okay. I will continue, but please stop me at any point and ask question if it's, as I mentioned, I'm a bit rusty about all this analytical side of, as some years has passed by. So please interrupt me and ask question if it's not very clear. Okay, so now once we have this divergence technique included in our system, we have enlarged the system, and now we proceed to try to find the symmetrizer. I'm here just illustrating. We managed to find an object H that, similarly to Maxwell, depends on a vector variable T. But now also, as I mentioned, as the K depends on F, then the H also depends on the background electromagnetic field. So we managed to find this H that produced this bilinear form here, which looks quite complicated, but you can check yourself that, well, one can see from this that this object is symmetric in alpha and beta. And also in yellow, I'm showing the additional terms due to the inclusion of the divergence cleaning field. And so this is about the symmetry of the H, and now we need to ensure that this is a positive definite bilinear object. So what we found is that if the background field satisfies force-free condition, so G is equal 0, the first algebraic invariant, it's 0, this is E dot B equals 0, I remember, and F being positive, meaning that it's magnetically dominated, then there exists a time-like vector U that satisfies this condition. And so that we can use this U, this field, this time-like field, to particularize this H. And if we also choose, we need to prove that there exists a W that we will choose also as U, the covector U. And for that, we can show that this is a positive definite quantity. So that's good, but it is only restricted, or it relies on that the field should be force-free all the time, I mean, everywhere. Again, this is something that mathematically it is true, that if you are within the force-free, you will continue being in force-free, but numerically you might depart from that. And so we wanted to ensure that the symmetrizer, it's also well poses of the system is also true outside of this constrained surface. So you can think this of a constrained surface. The theory is only defined there, but now we want to extend this system of equations outside this constrained surface. This extension outside the surface is completely arbitrary because there's no physics there. We only know the physics inside the constrained surface. So in principle, there is arbitrary how you extend the system, but we want to extend it in a way that we can guarantee well poses even outside of the constrained surface. So the idea we found was to replace, modify, or extend the F outside of the constrained surface. This way, we redefine F like this, where this sigma here is a particular combination of the two invariants. And with this construction, you guarantee that the F tilde now satisfy by construction the two force-free conditions. So by construction now, the F tilde satisfy the force-free condition always. And of course, you can check that when you are on the constrained surface, this F tilde reduced to the original F. So that means we are extending very naturally the system outside the constrained surface in a way that, of course, if we the system coincides, is the same in the constrained surface, but we modify it this way outside. And this construction guarantees or allows us to very easily find the symmetrizer outside of this surface. Because now, again, since this is always holding, then we can find this U tilde now that allows you to construct the symmetrizer. Okay, so that's we essentially rely on the previous result, but now we have find a way of extend the system in a way that by construction you can always guarantee this symmetrization process. Okay. So finally, at this point, we had our well-posed evolution system for the theory we wanted. We can consider to try. Of course, we do not want to depart much from the constrained surface, so we enforce this numerically additionally. But the idea was to have a well-posed formulation, even if you depart a little bit outside of the surface. Okay, so then I will try to describe a little bit the numerical code. It's called Onion. You will see why in a minute. As Oscar was commenting, it relies on the multi-block approach. So essentially, the idea is that you can foliate the space, three-dimensional space, by a series of spherical shells. And to do so, as you might know, it is not possible to cover a sphere with a unique regular grid. Only one regular grid. You might notice that the spherical coordinates, that will be an example, are not regular everywhere. They have this singularity at the pole, at the axis, the polar axis. So in particular, the idea is to use these 6 patches, 6 grids like illustrated here, to cover the sphere. This choice has shown to be.
Fede,
Sí.
maybe we can
Sí.
make a break now. I think it's a good
Okay.
time before you start
Okay,
with the
perfect.
code.
Yes.
Okay?
Yes.
Okay. So we will continue at 11:20. Okay?
Okay.
Okay. The Zoom is not working now. Okay. Fede, do you hear me?
Sí.
Okay, 11:20. There is
Dale.
a problem with the Zoom, so I want to make sure that it works.
Ok, pero estaban siguiéndola, ¿se veía o no?
Yeah,
¿Se cortó?
yeah.
Okay, okay.
But for the recording, I think it's a problem.
Okay. Six grids to represent these spherical layers by identifying this size of these 6 boxes, these squares. In this way, like to produce a box, right? Like And then if you think you inflate this box into a sphere, you can identify the coordinates on these 6 patches to represent a spherical surface, right? So topologically, you are building a sphere, and you just identify the coordinates appropriately to represent the sphere, the unit sphere, let's say. And these identified sides of the squares represents interfaces, grid interfaces, and in particular, in this case, they are only sharing the touching sides, right? Only one side of points are connected, are touched, and the other points of each square are independent. So this is particularly good for it provides an initial degree of parallelization. You only need to transmit the information among the different grids, so you can parallelize by using MIP technique for parallelizing or computing individual each of these squares. And you only need to share information about these overlapping grid points. You can then think, so this is one sphere, and then if you add then the third dimension, this third coordinate will be like representing a sort of radial coordinate, and this way you can foliate, as I said, like a sequence of spheres filling the space. So there will be an inner spherical boundary and an outer spherical boundary in this domain so constructed. In principle, we have these 6 grids, but then of course we can further parallelize this by adding additional layers, starting from the larger, the outer sphere of one domain that touches the inner sphere of the next layer, and so on. So you can construct multiple layers, multiples of 6, of course, layers this way, and it all relies numerically by the use of high-order finite difference scheme, and in this case, construct by summation operators, finite difference operators that satisfy summation by parts. You have probably seen this in the course. So the idea is that you can control the energy norm, some energy norm at the discrete level with these summation by parts operators that play the roles of integration by parts. So with that, you can control the points, the inner points. You are left only to complete the stability. You need to make sure that the boundary, there are some boundary terms, and these are handled by the penalty technique. So the idea is that for these boundary terms, you prescribe the incoming physical modes, characteristic modes of the equations by these additional terms in the right-hand side of the evolution equation. So you have these particular terms with this particular structure, which are based on the characteristic structure of the system, the characteristic decomposition. So they capture the physical incoming modes. For instance, in the case you are considering an interface between two domains, two numerical domains A and B, say. Physically, I mean, conceptually, the idea is that you will prescribe the incoming modes into the domain A by matching that with the associated outcoming mode from the neighbor domain. So it's the same characteristic mode into the two sides, but for one domain it's incoming, and for the other perspective of the other, respect to the normal surface, for the other is outgoing. So you essentially, with these penalty terms, you match the incoming modes to one of the domains to the outgoing modes in the neighbor domain. And these guarantee you to control the energy at the discrete level in the full domain. So this is more or less the core idea of this code. And this has a very good advantage that is very well adapted to problems in which we have, for instance,
can you enlarge the
oh, sorry.
slide?
Yes.
Thanks.
And this is very good, very well suited for problems like in which you have a central compact object. Let's say it could be a black hole or a neutron star. The black hole is easier in a sense because you can place the horizon inside the inner numerical boundary, and doing so, you essentially do not need to prescribe any boundary condition at the inner boundary, because there are no incoming modes from the perspective of the exterior of the black hole. The black hole horizon, all the modes are going into the black hole horizon. So then there is much easier to prescribe this boundary condition for the black hole case. And for the neutron star case, we needed to work further, because then you need to represent this perfectly conducting surface at the neutron star surface. So for that, I will describe a little bit these techniques we use to deal with the boundary condition for the neutron star, relying on this penalty technique as well. So I will come back later to this. Now the plan was to show like a tour of the code. Maybe a little bit brief and trying to make the central points. I mean, the code is large, has all these many files, but I will go through the main ones and explaining more or less the structure. At least that's the plan, and you can stop me at any point again, and we can discuss. So there are two ways to modify, in a sense, the conditions of the code. One is at the compilation level, let's say, at the compilation stage, which is by changing some parameters in this, some macros defined in this file. Here, you define the number of grids. You define, for instance, the particular theory you want to evolve, because in the process I keep the original vacuum Maxwell theory, or you can have two versions for free. All different kind of options, that are defined at time of compilation of the code. Also, the code, sorry, is written in C, is C language. And all these parameters you can define at the time of compiling. You can choose your finite difference operator, your dissipation, many choices you have. Once you define all of these, you define here, the equations. As I said, the derivative operators and so on. Runge-Kutta, for instance, the time integrator. So all of this is defined at time of compilation. And there are other way of modifying to run at time of running the code, right? So there are these input data file that the code will read when it starts running. And here you can prescribe many of the different parameters for a given run. So these are the time, initial time, finite time, the dimensions of the numerical domain, for instance, the mass of a black hole, the angular momentum of the black hole, the intensity of the the initial magnetic field, the type of initial data, etc. These kind of decisions you make at the time of running the code, right? And the central, the core of the code is this file onion main. So this is essentially the code, and it will start reading defining all the namings of the. Well, it will start defining the topology. It will start producing the different MIP domains, assigning each of them one processor. So as I mentioned, each numerical grid will run independently in an MPI process, and they will only share information of the interfaces among the different MPI processes. So all of this is handled in the central function, the main code. Here, all the variables, the fields are allocated. All the memory allocation is happened here. The input and output is handled by, or the output especially. I mean, the fields are written into silo files. This is a particular library to handle this kind of structured data. Essentially, it will provide the grid points and the different field values. Okay, so once we are here, you need to think you are like inside one of the grids, and only the part of the information is shared with the other ones and received from the other grids to compute these penalty terms and so on. Let me see. Okay. So something I forgot to mention. Once we have this grid infrastructure, these coordinates on each of these domains or subdomains, we know how to map. We use an auxiliary fields that will represent the space-time metric that has the information, the gravitational information of the black hole, let's say. So this is like an additional field that is like an auxiliary field, and you can simply construct the metric inside or using the coordinates of each of these grids. So this is part of the code is doing here, is building the geometry. Here it calls the function initial data. It provides the initial data according to the choices you have made in the first macro and in the data file. It defines which is the initial data. In this case, for instance, if we are thinking in the neutron star case, we have the initial data associated with the initial dipolar magnetic field configuration, let's say, or in different scenarios, you can decide which initial configuration for the electric and magnetic field you want. So, for instance, there is a first writing in the output on the silo files for this case. So this block is an interesting idea. With it, we want to. So this code has a checkpointing in the sense that as you are running, from time to time you write these output files, these electric, the fields. Essentially, you write them in the silo files, and so that means you can restart the run from any time level you have written in the data you have outputted. This is an automatically way of handling this if let's say the cluster ends there is a shutdown in the electricity or so, and the code relaunches itself at some point. It will read the last time step you output, and will resume the simulation from there. So there is this choice of starting from 0 with the initial data function, or starting from a previous simulation. What else? Okay, this is posterior. I will hide this one. It's associated with the, as I mentioned at some point, we then later extend this code to consider a binary system. So this is part of the implementation of the binary system, but for the moment it's not important. Okay, so here we reach the core of the function, and then the central loop where the time evolution is occurring. And then here, this is the function that integrates in time. This is choosing the time integration, in particular Runge-Kutta integration. And it will compute at each of these Runge-Kutta steps. It will compute the right-hand side of the evolution system, and include all of the necessary modifications to the right-hand side, namely the penalty terms or such in the. I will go there later. Okay, so then it do all the time steps. It at each time computes the right-hand side, all the modifications, and integrates, compute the global energy. You can check some global quantities to see the code is working properly, and so on. And up to the code that finishes, and erase this file and start liberating all the memory, and so on. So the central part is this, the integration function, that essentially is when computing the right-hand side in this file, onion.c. So this function essentially is the one computing the right-hand side for all of the points in the domain. So what it reads, let me see. So we can say that the main aspect here is that it starts by taking all the relevant finite differences, all the derivatives necessary, like the divergence of V. This is all collapsed, right? So this is the loops in the three-dimensional loops, taking the derivatives by using these summation by parts operators, finite difference. And here's dissipation is included. Okay, so here's important. So this is the bulk of the grid. So for these are the inner points, and then it calls the file equation .c, which is here. So here is where the right-hand side is compute, the general one for most of the pods. So you see here the metric is invoked. The fields are uploaded. And here you can see the right-hand side of all the fields. This phi is the divergence cleaning field, and this is B is magnetic field, and E the electric field. So of course it uses all the previously computed derivatives, spatial derivatives, and it incorporates all the terms associated to the right-hand side of the evolution equation. This was just, I think this is just Maxwell, the linear theory, and then we add, if we have force free, then we add a lot more of additional terms. You can see these extra additional terms. Of course, involves additional derivatives and so on. Here's some pieces that take care of these additional dampings we need for ensuring especially the algebraic constraint is preserved. And here is where numerical dissipation, Kreis-Oligger dissipation, is incorporated to the right hand side. So that's basically the right hand side calculation for the bulk, all of the points. And then we need to deal with this MPI information sending and receiving from the faces, the interfaces among the different domains, the subdomains. So here is where we apply for each of we are inside one of these subdomains. We are receiving information from the neighbors domains. And so we will essentially implement the penalty terms we need. So it goes to this phase. .c, I don't know if it's here. Okay, it's here. So along the way, there are many functions which are defined in different other files, of course. General functions like contractions or matrix or vector multiplications and so on and so forth. There are functions like geometry download, for instance, that also brings the metric, this metric field we have in like auxiliary field, downloading the fields, the evolution field itself. And here is where we compute the penalty. So this is essentially the difference field between the subdomain we are in respect to the information coming from the neighbor domain. We do this subtraction of these each of the components of the fields, and then we will apply the penalty terms to each of them. So for that we need the characteristic decomposition of the equations. Okay, so more or less that is essentially all what is happening here. So remember, this is only applied to the interfaces, and at each of the interfaces we do this. So this is, for instance, x, the initial x, the final x. So all the sides of the box of each of these boxes. In particular, there might be a special surface for the case, as I mentioned, when we want to represent the neutron star. The coordinate sheet here is the radial coordinate of these cube sphere coordinates, these multi-patch coordinates. So this initial radial surface is where potentially the neutron star boundary conditions should apply. So this has a different prescription in this case. While all the others are typically just interfaces between the two different subdomains. And one additional comment is, of course, there are many more details on different functions here, but I will only mention one additional function with code we developed for post-processing. So it essentially mimics the main function. It do all the same. We can read the results from the evolution at the time snapshot we want or we have. We can read these fields and start doing some additional computations you want to do, like a post-processing. Let's say you want to compute the electric current or the charge density or the Poynting fluxes, for instance, the luminosity to understand what the plasma is doing or how the energy is extracted and propagated away in the magnetosphere, so on. So we do all these kind of computations with this like separate code that essentially has the same structure as the onion, but it more, I mean, you can run it independently to try different like post-processing options, right? Okay, so sorry, maybe it was a bit too short. Maybe you have some question about the code, or otherwise I will move to show some of the results. Can you hear me? Can you confirm everything is working, or?
Here, whether onion is a code or a model. Is a code.
Yeah, onion is a code. Yeah, exactly.
It's a code.
It's a code. Perhaps the main feature is this representation of the space around the spherical shells. Interesting. And all of the parallelization and all the sophisticated summation by parts operators that Oscar has developed during the.
Fede?
Yes.
Yeah, there are here. There is a question here. Why is this a good approximation for magnetospheres?
Okay. Okay, so let me go back then to the motivation. Maybe it was a bit too short. So the idea is that no, this is not. The idea is that there are many relevant astrophysical scenarios, as the one I discussed in the motivation, like pulsar magnetospheres, or especially pulsar magnetosphere, which is very well studied and more or less well understood. But also in other relevant contexts like AGN, producing these huge jets, in which you can justify the validity of this approximation. And the reason is that you cannot have a vacuum, as we argued here, because the rotation, for instance, in this case, the rotation of the central object produced these very strong electric fields along the magnetic field lines that will produce this particle generation cascade. This is quite well understood now. And this process, as I mentioned, it self-regulate itself in the sense that as long as you have enough plasma, then you will screen this electric field that was accelerating the particles, and you will no longer produce further plasma, further particles. So that makes also the possibility to justify that the plasma will remain dominated by the magnetic field, because the plasma will, compared to the energy of the magnetic field, will remain very like tenuous and made of very light particles. So it is quite reasonable that in this context, the plasma will very quickly accommodate to cancel the Lorentz force. So, and that is what justifies the force-free approximation in these scenarios. Of course, we are talking about the exterior of the star in this case, for instance. To model the interior of a star, you need a lot more. Even MHD, it's better, but still, it's not enough probably to have a good description of the interior. But for the exterior, we have this boundary condition at the neutron star surface, which is a very good approximation, and allow us to argue that outside the neutron star you will have this force-free plasma. There are, of course, I should mention perhaps that there are more sophisticated evolution system, more sophisticated, I mean, even respect to MHD. These are the so-called particle in cell simulations, which describe like a mixture method between evolving the electromagnetic field and representing the particles itself to some extent, evolving the dynamics of individual or group of particles, I should say, on a grid together to coupled with the evolution of the electric and magnetic field. So the particles will evolve with the equation of motion for the particles, considering the background electromagnetic field, and they at the same time will be the source of the evolution of the electromagnetic field. So this more self-consistent methods has been developed, and in the case of pulsar, for instance, it has allowed to better understand the theory. And one of the main conclusion is that force-free electrodynamics is still a very good approximation. Most of the magnetosphere, except for some small regions in the magnetosphere where you have there is no enough plasma, for instance, and you are producing particles, plasma. So this happens dynamically, and you have these regions where particles are accelerated, and then it's of course what it was understood before.
There is a question in the chat. I just wanted to.
Oh, okay,
how do
sorry.
you define the star envelope?
Sorry?
How do you define the star envelope?
The crust, the surface of the neutron star. Okay, so the neutron star is a very complex object, and I'm not really an expert, especially in the interior. It's very complicated. But I know that there is supposed to be a crust, a stellar crust. So it's kind of a solid, highly conductive surface, like iron. I don't know, maybe I think it's iron. Well, at the time of the star birth, after a supernova, let's say, it at some point freezes. This crust freezes, and in this crust, it freezes the magnetic field, which remains attached to this boundary, to this surface, this conducting surface. So for us, the interior and the exterior of the star means you are inside this conducting crust or you are outside. This crust provides a very good or natural description for the boundary conditions. So we are in the code looking to the exterior of this. We are assuming that there is some initial magnetic field freeze in the crust, and from the perfectly conducting hypothesis or assumption, we can derive the boundary conditions for this. So we only evolve the plasma outside the neutron stars, this surface, which we will identify with our inner boundary of our numerical domain. And at that boundary, we will develop the boundary conditions appropriate to deal with this perfectly conducting surface. So for us, this is the classification or the description. Of course, in reality, it's much more complicated. But yeah, I don't know. Are there other questions? Or? Yeah, please tell me about the question, because I really don't see the chat here. So typically not. I don't realize about the question. So you please read to me.
Yes, I will tell you when there is a question.
Okay.
You need to, but there is a button there to see the chat. But yeah, but I can see it, and I will tell you when there is another question.
Okay, thanks. Okay, so maybe I should go back to. Okay, so now, after this very brief tour on the code, I will just perhaps briefly mention this part because it's a bit too technical. Maybe I don't know how interesting it is or not for you, and then I will jump to the numerical results. So as I was saying, this surface for the neutron star is very delicate. It's very important to appropriately define and implement the boundary conditions on the neutron star surface. Typically, boundary conditions is an important part of the modeling, numerical modeling. Sometimes, or most of the times, the boundary conditions are farther away, and people, so then you can do more rough approximations. But for this case, this is very delicate because the neutron star or close to the star is where most of the dynamics is happening. More the fields are more intense there. The dynamics is more strong. So really, you need to work this appropriately to represent this boundary here, especially this one. So the idea is to use the same infrastructure with the penalty terms, but now instead of having this neighbor domain B, we have like exterior domain, which is not, in this case, would be the neutron star, let's say. And so we need to figure what is this operator here, L, we need to put in here. So conceptually, we know that to prescribe boundary condition is to provide, or what you can, the thing you can define is, or you need to define or prescribe is the incoming characteristic modes to your domain, right? So the structure of the operators we propose for boundary is essentially this. This is the code base associated with the incoming modes. So this will pick the outgoing modes, so from the domain perspective. These are the ones you want to prescribe. And we will prescribe them based on the outgoing modes. And of course, some external source that should represent the magnetic field inside the neutron star. But the physical condition there is related to this perfectly conducting surface. So the physical condition we know we should have is the jump conditions. We know the jump conditions for the co-moving electric and magnetic fields on this perfectly conducting surface. So plus represents the exterior, the field we are, the ones in our numerical domain, and the minus represents the ones in the perfectly conducting crust of the neutron star. So in particular, we know, since it's a perfect conductor, that the E minus should be 0. The co-moving electric field should be 0 inside the conductor. And the boundary conditions, or these jump conditions, the only thing freedom they allow is this charge, surface charge and surface currents that could be induced in the jump surface, right, in the conductor. So essentially, what we know is that the tangential electric field must be continuous and equal to 0, because inside the conductor, the co-moving electric field is 0. And the normal component of the magnetic field should be also continuous and equal to the one inside or freeze into the stellar crust. So which will be generically some function of the coordinates. Sorry, I forgot to present. So physically, are the kind of conditions we want to impose this, and for this we will rely, as I mentioned, in the penalty technique by proposing these boundary operators that combine the different outgoing modes to prescribe the incoming modes. So in the end, when you go to the fiducial observer, not the co-moving observer, but the fiducial observer, you have this kind of boundary conditions. So these are the components you want to enforce. So as an example, I will describe Maxwell case to fix some notation. So the U represents all the fields. It's divergent cleaning phi, the electric field and magnetic field. And these are the co-base associated with the fields. So this is some notation. So these are given a vector field A. This will be the normal component. This is the two perpendicular tangential components. And these are the characteristic modes of the vacuum Maxwell equation. So essentially, the fields are transversal to the propagation. This is why we see here these P and Q, which are the two independent transversal components of the field. And so for in this case, to have a perfectly conducting interface or boundary condition, it's similar to having a mirror, right? So these are the most general boundary operators, and to fix the conditions you want, that namely you want to fix the tangential components of the electric field. So that completely fixes these freedom parameters, these particular combinations. And physically, once you solve this and see what are these parameters, which are these particular values, you can reinterpret this as essentially this mirror I was telling about. So essentially, all the outgoing modes, you are going to reflect them back to the domain. So that would be an example in electromagnetism. And this way you see the operators enforce both components of the transverse electric field to the value you want, in particular since we are not in the co-moving, this is not zero, but some fiducial value of the electric field. Okay, so here is just not the idea you to follow all these calculations. These are the characteristic decomposition for force-free electrodynamics. So now there are some modes which are transverse, as the ones in Maxwell, and these two here. And there is also these Alven modes, which are also a particular limit of the usual MHT Alven modes. And we have these two modes are the combination of the constraint mode associated with the divergence free of magnetic fields coupled to the phi, to the divergence cleaning field. So now here we explicitly see that the thing I mentioned initially, that this divergent cleaning field couples to the constraint and make it propagate non-zero speed. And this additional mode is associated with the constraint of force-free electrodynamics, namely E dot B equals 0. So these are all the characteristic modes of the theory. And we play the same game, of course, as mentioned before. Now you see that the characteristic vectors and the characteristic co-vectors depends on the field, on the background field. So it's more complicated than in Maxwell case. And yeah, so this is mentioned here. both fields appear in the basis and in the co-basis. So also the coefficients might depend in the fields as well. But the good news is that you can play these games, and there is a unique, when you want to enforce the tangential components of the electric field, there is always a unique combination for these coefficients, and you can find the boundary operators. There are many more details about the possible degeneracies in between these characteristic subspaces. Sometimes, for some particular values of the field, they sometimes how do you say, collapse. Some different subspaces collapse, but since the theory is symmetric hyperbolic, as we show, there is always a complete set, a complete basis, characteristic basis, and you can actually always find the appropriate boundary operator for this. Okay, so here's some other detail about there is some additional additional technique you need to use to also control the constraints in the boundary. But I will probably not discuss this today. It's based on this idea from this previous paper from Oscar, Mariana Cesare. But okay, so this is like an additional. So we impose the physical conditions of a perfectly conducting surface through the penalties, and we use this additional technique to control the divergence, the constraint in the theory at the boundary. Which again is crucial here because this surface is the most relevant region of the domain around the neutron star, is the most dynamic region of the magnetosphere. Okay, no, maybe if there are some questions about this, because now I'm moving to the results, to numerical results. Yeah. Okay, so I will briefly discuss some of the main numerical results during these years after my PhD. So once we incorporated the boundary conditions for the neutron star, we started looking at the pulsar solution, like a good starting point. And in fact, it was only very recently that the GR effects were incorporated in some of these studies, but because typically they rely, or they were compute these pulsar magnetospheres, force-free magnetosphere, were computed in Minkowski in flat spacetime. So we were here incorporating the gravitational field, right? So we study the different configurations. There are a few physical parameters, like dimensional parameters. One is the inclination angle. There is an angle between the magnetic axis of these dipolar fields we assume for the neutron star and the rotational axis. So this is one of the few parameters, and the other one is the angular velocity of the neutron star, computed by this ratio between the radius of a star and the radius of a light cylinder. And also in our case, since we incorporate the curvature of the gravitational curvature, we have this compactness parameter, which measures the ratio between the mass of the neutron star and the radio and its radio. For this, we studied like different configurations and explore a little bit the effects or the impacts of the gravitational field on the luminosity, on the spin down luminosity of the pulsar. So then we also consider this different scenario where we have a neutron star that is just moving across a uniform magnetic field, an exterior magnetic field. So this is relevant in the context of, for instance, you have like an accretion disk, and you have a system or a neutron star that is moving relative to this exterior magnetic field anchored on the accretion disk. There were some previous works. We knew this configuration also produced a jet, like in the AGN context for the black hole. So we found this interesting and decided to use our code to implement this, to study this. And indeed, we found that for the neutron star, similar current configurations are produced as the one known for black holes, and that you can produce these jets as in the. So in this case, we can consider either by turning the mass parameter on and off. So this is for mass in Minkowski, so mass equal to 0, and then we can turn the mass of the neutron star on, and we see this very similar, but there is an additional effect on the trailing magnetic fields behind the neutron star motion that produce an additional current sheet behind the neutron star. And again, we studied more or less the properties of how the Poynting flux luminosity is scaled for different velocities. Then we also explore the magnetar scenario. Magnetars are very, very young neutron stars with very, very high magnetic fields at the surface, in the order of 10 to the 14, 10 to the 15 Gauss. And are really dynamic objects since they are very young neutron stars, so they have a lot of phenomenology associated with this very strong magnetic field, and give rise to different kind of transient signals, like flares, for instance, or so. And from the model perspective, one possibility is to consider. So now these are typically very slowly rotating neutron stars, but since they are young, this crust sometimes is exposed to very high stresses from the very high magnetic fields. So this could lead to crust failures in some regions of the stellar crust, and this can be modeled by our boundary conditions. So locally, you can inject some sort of twist associated with these crust failures in the surface. So you inject this electromagnetic energy from the surface, and you can study how this how it propagates within the magnetosphere and how it behaves. So what we found, we extend previous work into axial symmetry to the full 3D scenario, and we confirm that indeed there are critical twisting angle. The intensity of this twist of the footprints that produce. If you are below this critical value, you can produce a sequence of equilibria in which you can accumulate, store this energy within the magnetosphere, but nothing really happens. But if you twist the field's footprints beyond this critical value, then suddenly there is an instability in the magnetospheres. The magnetic field, the twisted magnetic field lines expands very suddenly, and then they reconnect and they eject these plasmoids. And these are related with these transient emissions that we see from magnetons. So, okay, so this was this study on magnetars. Now let me finally move to the binary system. Okay, so for the binary system, what we did was to since I mentioned the code is actually well suited for one single compact object, central compact object. But since we have these boundary conditions for the neutron star developed, what we realized we could do is to include the space-time associated with the black hole through the metric in the domain, and keep the neutron star in the center. So we can impose the boundary conditions we know how to do for the perfectly conducting surface. In principle, we will not consider the gravitational curvature of the neutron star itself, but only represented by the Kerr black hole that will be moving around, orbiting around this center in our code, right? So the neutron star is prescribed or modeled in the code by the conducting boundary conditions, and the black hole is represented by the metric. And this way you can prescribe a given orbit. Let's say in principle we were just focusing on a Keplerian circular orbit. And we study different orbital separations, and we study what is the electromagnetic dynamics of this system with the plasma, of course, in these compact binary systems. So more or less you can see the dynamics, how the presence of the strong gravitation of the black hole. The black hole is the black's surface, and the neutron star is represented by the gray surface. The lines represent some fiducial electromagnetic field lines, and the colors represent the intensity of the magnetic field. As you can see, as the black hole passes by, it highly distorts some of the magnetic field lines, producing these huge reconnection events. Magnetic field lines produces kind of current shifts, as we saw in the pulsar cases. And they reconnect, magnetic field lines reconnect, and eject a lot of electromagnetic energy this way and release it. So we can study how this energy extraction process will be happening again. So this is similar to the original ideas of Blanford-Snayek and Goldrich-Julian. You have this mechanical energy, in this case of the orbital motion, that we can extract through the conducting plasma surrounding these objects. So it's reconfigured in the magnetospheres, and it's eventually emitted away in the form of electromagnetic radiation. So this is relevant in the context of this new so-called multi-messenger astronomy, which, as you know, rather recently from 2015, and then in 2017 it was the first detections of gravitational waves, and 2017 was gravitational waves coming from two neutron stars that merge. So it produces a very strong, observable gravitational wave. And it was also observed in the electromagnetic band, in all of the electromagnetic spectrum. So it was a very impressive event, and it serves to study a lot of these details of these models. So the multi-messenger refers to the possibility. So typically astronomy was based everything about the electromagnetic emissions and observations. So now we have these new windows of gravitational observatories, and these two signals combined are very strong and powerful to allow to extract a lot of the physics. So this is more or less the motivation to study the possible or potential electromagnetic emission in these binary systems. Okay, so these are some details which I'm not not too much relevance. We again study, typically we consider the kind of luminosities you can extract from this system for different parameters like the orbital separations or the spin, etc. We also consider misalignment between the magnetic axis and the orbital axis and so on. This is an illustration of one of these cases. Okay. Yeah, but roughly speaking, this is more or less the motivation to try to explore the global dynamics through the force-free simulation in these specific scenarios, and then model on top of this, or based on these global solutions we have for the electromagnetic fields, try to model the actual electromagnetic emissions to characterize or have a good characterization of the potential signatures, electromagnetic signatures in these systems. Since force-free do not accommodate for the acceleration, as I mentioned, part of the approximation is using this fact. So this is why we need to model on top of this global solution, we need to further model the potential emissions by modeling the microphysical aspects and propagating this with a ray tracing code that probably you have heard from Joaquin. So this is sort of the idea or the program here, to first study the dynamics of the surrounding plasma, have some notion of the global solution, and then from them try to model the details on possible electromagnetic emission. So, okay, so I think that's more or less it. Thank you very much for the attention, and open for questions now. I'm still connected?
The- yeah.
Okay.
There is a question here. I will hear and then translate to you.
Okay.
The microphone. Oh. Uh-huh. Okay. Yeah, the question is in this image, what happens there? This image is, you get all the simulation. Yeah, it's very complicated. And then you put in the visit, and you follow the lines, the magnetic field lines. Yeah, so you put a lot of points and say, okay, follow now the magnetic field lines. And so what you see there, these lines are the integral curves of the magnetic field.
Exactly.
Field lines.
Exactly.
Okay.
So we have the electric and magnetic field at each time, and in BSID we can compute. You give the source points, you provide the source points, and BSID will integrate for you the following the magnetic field lines. And this is a rough way of trying to understand the dynamics. And of course, usually it's very complicated. It's three-dimensional and many different parameters. But this is a typical efforts to try to understand what is going on.
Yeah, it is. So the simulation is a huge thing. It's a lot of points, a lot of numbers there. In every point you have the electric field, the magnetic field, the current, the charges. And so you have to now analyze to see what it is in there. And this is a lot of intuition. And the most relevant thing always is to get how the magnetic field goes, because the particle goes around the magnetic field.
Mm.
And the big effects are the reconnections. So these are places where you have two lines, magnetic fields, in opposite direction, and they connect like this, and then they reconnect. This goes with this, and that creates a lot of energy. So that's what you are looking in this. These ones there, the red things.
Exactly. So here we are focusing also the attention on the current sheets. So these, because we know from the pulsar. So the idea always is to rely on the ideas or the understanding from pulsar theory, which is more developed and where it is more observational data available. So we try to rely on these pulsar ideas and extrapolate them here in the context of a binary system. And typically in the pulsar, the most active region of emission regions are the current sheets and the reconnection associated with the reconnection. So typically in here, we also want to try to understand what are these configurations of the current sheets. And here the red and the blue both are pointing or signaling the current sheets.
Yeah, the current sheets are places where the force-free approximation breaks, because the magnetic fields, they get discontinuous, and they create a lot of electric field. Exactly. And so what we do to keep there is a lot of dissipation, physical dissipation, that we model, saying, okay, the electric field now is going to be reduced. Okay, so we reduce continuously the electric field. And these are for instance, this red line that comes like this. This is our region where this is happening. And so in the reality, in these places, you have particles that are accelerated. So you dissipate the electromagnetic energy by accelerating particles. And these particles then generate radiation that we see. So these are the places where you see radiation. So then you model how the radiation comes from those places. So this is how it is done. There is there is a lot of modeling. That is, when you finish this, there is a modeling on what you will see at every point. And then this radiation has to be transferred to very far away, so that you see in the telescope or on a satellite, you see something and you say, okay, you will see some spectrum and some periodicity, some curve lights that will say, okay, this is what we are seeing. These things are rotating, and every so many seconds you see a peak in this way. So there is a lot of things there to understand. Even after you did the simulation, there is a lot of processing of this.
Exactly. Yeah. What I was that was the reason I mentioned this post-processing code.
Yeah.
Because it's very helpful in this post-processing of the solution. You are not done when you finish the simulations. You need to try to understand and analyze. And this post-process code is very useful because it runs very quickly and try different things. You can output different quantities that you can then look in visit and so on. So it's
in the code, when it runs, it only stores the electric and magnetic field, basically, and these 5 fields for the divergence cleaning, so that we know that the constraints are kept there. The errors in the constraint. And then we take this data and post-process. So from the electric and magnetic field, we get the currents, etc. We also save where we make in what points in the space we make this, have to reduce the electric field. So these are the places where the current sheet is. and there we get the charge and the currents. And from there, then there is another step. You say, okay, from this, I want to get what is radiation is away. And this is done with some other code. Particular, Joaquin made, we have also a code that takes.
Oscar, you are muted. Muted?
Okay. More questions? Yeah. Didn't?
Sorry, you're muted? You couldn't hear the question.
So, first of all, thanks. And my question is about the angular momentum of the electromagnetic field. If it is conserved in some way, or if it switches from the compact objects to the electromagnetic fields, and vice versa, if they decay or if they oscillate.
That's a good question. I mean, so typically, if you assume everything, if you were allowed to remove the current sheets, then in the bulk of the domain, in all the space-time around the two objects, the stress energy tensor is, you can define a conservation. You have a conservation law, so both the electromagnetic energy and its angular momentum are both conserved. But of course, there could be some, either at the boundaries of the involving the two objects and in the current sheets, which are really there. So in the current sheets, you lose this conservation because you have some, in some sense, interaction, energy transfers to the fluid. So then you lose the conservation law. You might try to partially recover that by keeping the track of this electric field you are removing, so then maybe you can make sense of the dissipation. And also you have this the effect or the possible fluxes into or out from the compact objects. But other than that, yeah, in the space around is concerned, we haven't really. So the honest answer is we haven't looked much into what the angular momentum, electromagnetic field angular momentum is doing. We only typically look at the energy, the Poynting fluxes and the energy being dissipated, but we don't typically look at the angular momentum.
Okay, thanks.
Sorry about the partial answer, but really we haven't. Maybe you want to add something, or you have something in mind, or?
Yeah, I was thinking about that because there's the Penrose process, right?
Mm-hmm.
So there's a way to extract angular momentum from these bodies. And I would also ask after that if there is a configuration that, and I mean, when you do these simulations, you are dealing with an astrophysical situation, but imagining if you could do that in some laboratory, what would be the best configuration to extract this angular momentum to maybe the electromagnetic field or the particles? If
Yeah, so typically, so as far as we have looked in this binary system, so the Blandford-Snijder mechanism associated with the Penrose process was introduced in the discussion in the spinning black hole case in the context of AGN, where the extraction really came from the orbital angular momentum, the angular momentum, sorry, of the black hole. In this case, as far as I checked, there are no really energy being extracted from the black hole, which in principle even it could be a Schwarzschild black hole. In general, we use a Schwarzschild black hole. So of course there could be some dynamical or effective ergosphere associated with the motion, but we couldn't find any really extracted energy from the black hole. The energy seems to arise. It's from the orbital motion, but seems to mainly arrive from the neutron star boundary conditions. From the neutron star. Typically, we couldn't find any significant energy being extracted from the black hole. Yeah, regarding the experimental side, I don't think there is. So this is why these systems are quite interesting, because typically there is no possibility of explore these kind of intensities of the magnetic field, for instance, in the laboratory. These are very, very magnetized, highly magnetized objects, and the dynamics of this plasma is typically the only way you can explore it is in these scenarios. As far as I know, maybe there's something more to say, but that's probably all I can say. So typically these astrophysical conditions are very extreme conditions, typically are not possible to reply in the laboratory. So, but maybe I'm missing something.
oh, thanks, and
Thank
thanks
you.
for the whole presentation also.
Thank you very much.
All this energy and angular momentum, binary system, that is smaller radius, right?
Yeah, of course. Something I didn't mention. Yeah, I didn't mention many things, but yes. So there is some important scale separation typically. Typically in this system, the gravitational energy is several order of magnitude higher than the electromagnetic energy. So even the electromagnetic energy is significant, and you can probably detect some in some cases. The gravitational energy that the system loses through the gravitational interaction is way higher than the one it will lose through the electromagnetic interaction. So typically we actually use these to prescribe the motion by hand, assuming there is following the gravitational spiral or gravitational motion. Using this kind of effective, we use this kind of effective metrics or space-times.
Yeah.
So this particular was simply a black hole, but in a recent work with a student, we were implementing an approximate metric to have both the masses of the two objects. Of course, it's an approximate solution, but the idea is that this solution would be like a background solution to the dynamics of the electromagnetic field, that even though that is strong, it's still several orders of magnitude weaker than the gravitational interactions.
That's clear, but I mean, in a cosmological times, this is going to make the system decay.
Yes.
And I guess it's stronger than the energy lost by gravitational waves.
No, the gravitational energy loss is typically much stronger than the electromagnetic one. Yes, exactly, yes. up to merger essentially. Yes.
Ah, okay.
because-
So this is not important, really.
I mean, maybe if you are considering two stars, maybe not too compact, maybe yes, you could, electromagnetic field could be important or significant.
Because
You
for
know.
a single pulsar, the decay, the spin down is due to the electromagnetic.
Exactly. In the pulsar, then it is exclusively electromagnetic losses.
Yeah.
But in this case, the bulk of the losses are from the gravitational wave emission.
Yeah. Right.
We use this as in our advantage because yes, we can use this like background space-time solutions and only focusing on the dynamics of the electromagnetic
Right.
field on the plasma. And this reduces significantly the numerical cost of this. Otherwise, you need to solve the Einstein equations together
yeah,
with the plasma.
it's another time scale. I mean,
Exactly. So
Okay.
this is kind of our advantage in exploring these systems. These are only very recently start to be explored. Of course, the gravitational wave detections are not too far away in the past, and these particular emissions would be precursor electromagnetic signals because they take place before the merger. And so these could be very relevant, and there are not many studies yet considering these scenarios. And the parameter space is very large. This possible orbital separation, masses, inclinations, etc. And so this scale separation and the way the fact that we can only focus on the plasma, it's very convenient.
okay. Question? Okay. Thank you, Fede. Nice talk.
Thank you very much. Thank you for the attention and
See you
questions.
next. Well,
You're coming back. Okay, nice. See you.
cold weather.
Yeah, prepare.
Okay. Bye.
Okay, bye bye.
Are there questions? We have 10 minutes. Maybe there is some question on the homeworks, on the labs. ¿No se puede bajar? It's the 7? Puedo bajar labs, sí. But maybe the path is